Hello students, this is Dr. Faizan Mirza. I am discussing respirometer with you and how respirometer can be used to measure the rate of respiration and compare the rate of respiration of different organisms and how it can be used to measure the respiratory quotient or RQ. Now, when we are discussing respirometer and RQ, we need to understand what respirometer is and how respirometer works. So, the respirometer that I am showing to you, it's a very simplistic arrangement of apparatus in which I am just using a test tube and a calibrated glass tube with a dye present here, and this is an airtight bung which makes sure that the air cannot enter, air cannot leave. I have placed my respiring organism here. I have placed a mesh here, and I have placed a cotton here which is having potassium hydroxide solution. So it is soaked in potassium hydroxide, and I'll measure, and I can measure the weight of the, or you can say the actual, I can measure not the weight, the mass of this soaked potassium hydroxide cotton before placing it. So I know the initial mass of this cotton, that how much it weighs. So I'll place my respiring organism here. You can see that I can apply Vaseline or jelly here. So a gel here, so not jelly, gel. So it will make sure that this container stays airtight. You can have various type of respirometers. So this is a very simplistic that I am showing to you. But every respirometer works on the same principle. So what's the function of this potassium hydroxide that I've added here? It will absorb all the carbon dioxide that will be released by respiring organism. We know it will release carbon dioxide as it respires. The carbon dioxide will not go out of the tube in the capillary tube, and it won't be able to push the dye towards away from the test tube, because the carbon dioxide will constantly be being absorbed by this potassium hydroxide here. So potassium hydroxide serves as carbon dioxide absorbent. What do? We take readings after 2 minutes. So we allow the organism to stay accustomed, or you can say acclimatized to the new conditions. We do not take any readings for 2 minutes. We let it sit for 2 minutes. Now once 2 minutes have passed, what I'll do, I'll note the initial position of the dye, and I'll just see where the dye is present, and I'll mark that position. Now I'll start the timer, and I'll start to record the position of the dye, for instance, after 10 minutes. So what I'm doing, I'm just trying to note where the dye moves after 10 minutes. So I'll calculate the rate of movement of this dye by distance upon time. So this is actually centimeters upon minute, not cube. So this is not centimeter cube. So what I'll do, I'll just measure the distance covered per unit time. So movement of the dye will be in the direction I have mentioned, x, because all the oxygen in this tube will constantly being used by the respiring organism. So the amount of gas in this tube will start to decrease. As it starts to decrease, the dye will be pulled inwards, because the air will be pulled inwards in this way. So, and since carbon dioxide is not being allowed to go out into the same capillary or the graduated tube, so carbon dioxide goes here. So as a result, the dye is pulled inwards, and we can measure the rate of movement of this dye along this direction. So I can just repeat this experiment for a different organism, and I can just compare which organism respires at what rate. So rate of respiration can be compared in that way. When we are doing comparison of respirometer, using a respirometer for different organisms, we need to make sure that the organisms weigh the same. So we need to take the same mass of the organism. For example, if I'm taking germinating seeds, if I'm comparing them with peas, or I'm comparing with an insect, or I'm comparing with insect larvae, or I'm comparing it with anything. So with any living organism, obviously. So I'll just need to make sure that the mass of the respiring organisms must stay same, and the time that I'm giving for them must stay standardized as well. The amount of carbon dioxide absorbent solution, which is potassium hydroxide solution soaked cotton, this also should stay the same. And what I can do, I can again, once this experiment is completed, I can just take this potassium hydroxide soaked solution out, and I can reweigh it. So when I reweigh it, I can get how much more mass has been added here. That additional mass actually represents how much carbon dioxide it actually ended up absorbing, because that increase in mass actually tell me how much carbon dioxide was released here, and it got absorbed into that cotton. I need to repeat this experiment at least 3 times to make sure that whatever respiring organism I used, this actually gave me the correct results, and I'll take the mean respiratory rate for that organism. So when I'm repeating, for example, if these were germinating seeds, so if these were germinating seeds, I need to make sure that I'll just repeat it 3 times with the fresh germinating seed samples, and they need to be of same mass. And if I'm doing it with the germinating seeds, so I need to make sure that I exclude the light source from here, because if light goes in, then the light will start to carry out photosynthesis, and it will actually push the germinating seeds to carry out photosynthesis, and that can affect my results terribly. So I need to make sure that if the germinating seeds or any photosynthetic organism is placed here, I cover it with the aluminum foil, or I need to paint it black or do something so that of scientific sort, obviously, to make sure that light doesn't penetrate in this region. Now, once the respirometer is actually help you with calculating the rate of respiration, what further can you do? You can calculate the respiratory quotient as well. We know what respiratory quotient is and how we calculate respiratory quotient. What do we do when we are doing respiratory quotient? We just take out the volume of carbon dioxide and we divide it by the volume of oxygen. So in this case, we know how much carbon dioxide is produced by weighing it. So we can use this formula. We can use this modality, that how much carbon dioxide increase in this potassium hydroxide, and I can just go for the change in mass, and I can calculate how much mass of organism actually release this much carbon dioxide, and per unit how much of carbon dioxide would it be releasing. Other way of how much carbon dioxide is basically produced, and how we can calculate the RQ values here. For calculating RQ values, we can go for repeating the experiment without soda lime. Soda lime is potassium hydroxide. So if I repeat the experiment without soda lime, so if carbon dioxide absorbent is not there, I'll be seeing that the movement of dye might be away from the apparatus in the direction Y, although it was in the direction X when carbon dioxide absorbent was being used. Now, if it is moving in the direction Y when potassium hydroxide is not being used, it means that volume of carbon dioxide being produced is greater than the volume of oxygen being used. That's why more carbon dioxide being produced keeps on pushing this dye away from the apparatus. The other case could be that the dye start to move inwards in the same direction as it was moving in X. This time it is moving in the same direction as X. I call it Z. Now, if it is moving in the direction of Z, it means that this is because more of oxygen is being used than carbon dioxide being produced. So less gas of carbon dioxide is pushing the dye further away, and more of it is actually causing the dye to move inwards. So as a result, I can say that if dye move inwards in the absence of potassium hydroxide, it actually means that volume of oxygen is used being more, and volume of carbon dioxide produced is actually less. So once I have these, I can calculate RQ by CO2 upon O2, and RQ actually is CO2 upon O2. In this case, it will be X minus Z upon X and X plus Y upon X in this case. And when these are just simplistic mathematical manipulations of this. In which kind of respiratory substrates would these values be found? We know fatty acids, when fatty acids are being respired aerobically, the volume of oxygen being used actually is greater than volume of carbon dioxide being produced. So we can expect the experiment of this sort. This is the kind of reading when I'm using fatty acids. Similarly, if I'm going for alcoholic fermentation, if alcoholic fermentation is occurring, we know that the RQ value rise above 1, it goes to infinity. So in that case, we'll see that it will start to move away in the absence of potassium hydroxide. So this is how respirometer can be used to determining the rate of respiration, and how respiratory quotient can be calculated from the same experiment by repeating it without potassium hydroxide and comparing the values and taking the measurements and then just mathematically manipulating them to work out the answer. That's it from my side. Thank you so much.